Oh, there. You are. Hi. I think that was funny. Ron. All right. So in the last recording, I endeavored to give you a mental picture of what an electric field kind of looks like. I totally get that you don't have anything close to a real good feel for it just yet, but hopefully the pictures that I drew give you a start. We're going to see lots and lots more of them as we go, so don't sweat it too much right now. Also, you'll see much better pictures in your textbook. You'll see them online, Google Images, all sorts of things, all sorts of ways to see pictures of electric fields. And a very important concept that I want to make sure there's two major important concepts that I want you to make sure you're very clear on. One is that the electric field is a three-dimensional phenomenon. It fills all of space. It's not just flat on the whiteboard, but it fills all of space. If I had a point charge right here, it would be creating an electric field, and what I want you to imagine is that that electric field fills all of space. It exists at every point in space. Okay, and indeed, that's exactly what the definition of the word field means. It is a physical phenomenon. The definition of the word field is a physical phenomenon that exists at every point in space and whose value is different at different points in space. And by value, I mean the magnitude of that is to say, the strength of the field at each point is different, and the direction that the field points is also, in general, different at every point in space. And in fact, the vector nature of the field is the second important concept I wanted you to get, that this field is a vector. Okay, and so so from this being our source charge, right here the field might point, for example, that way, but over here the field points this way, over here it points that way, up here it points that way, over here it points behind me, and so on. Okay, so three-dimensional phenomenon that is a vector phenomenon, a vector field, as we say. Right. So now that I've started enabling you to wrap your head around what the thing looks like, now that I've started wrapping your head around what a field looks like, I want to next go into the mathematics. How do we calculate the thing? And so I'm going to get a little mathy here. And the calculations that we're going to do will include both the magnitude as well as the direction of the field. Okay. So let's think about things. So let's suppose I have a dry pen. Let's suppose I have some collection of source charges, and they don't all have to be positive, and frankly, they don't even all have to be points, but whatever. So these are all source charges. They all are sources of an electric force. And in very, very soon, what I'm actually going to say instead is each one of these is the source of one electric field. And then the total electric field is going to be the sum of all of these electric fields, the superposition of all of these electric fields. But anyway, for whatever reason, these are our source charges. The source of the field, the source of the force. What force? The force on our test charge over here. Now, the thing that I want to calculate, the thing that I want to talk about, the thing that I want to think about is what is the total electric field at the location in space where our test charge happens to be located. The reason that I am asking that question is because with the model that we're creating, which is that the electric field of the source charges transports the influence from the source charges to the test charge, or to put it another way, the electric field of the source charges is the mechanism that transports the electric force from the sources to the test. But since the test charge is here, it's the field at this point is the thing that I need to care about, because I could calculate the field over here, and later on I will, but since there's no test charge here, who cares what the field is there? There's nothing there to feel a force. So you, in terms of the relationship between field and force, the electric field of the source charges versus the electric force that acts on the test charge, the point in space where we want to calculate the field is the point in space where our test charge happens to be. Otherwise, if we didn't calculate it there, we'd be calculating the wrong force. Okay. Well, I could draw the electric field of this negative charge and include the appropriate field vector from that top negative charge here, and then I would draw the field vector from this positive charge at the location where capital Q is, and then from this one and this one and this one, and I could do all that. And in fact, why not? So let's label these. Let's call this one Q1. I'm going to use little q to represent our source charges, and then capital Q is our test charge. And Q4 here, Q5. Q6, finally Q7. Okay, so we have a total of 7 source charges, and then just the one test charge. Okay, all right, well, why not? Let me draw the field vectors. Okay, so at this point in space, remember that the electric field of a point charge, and I'm just going to take these one source charge at a time. The electric field of a positive source charge is going to point outward, radially outward from this charge, and it will point away. Field vectors from a positive charge point away from the positive charge. So at this location, the field on capital Q from Q7 would point that away. Okay. From Q6, its field vector is going to point radially away from Q6. So if I don't want to draw it because it's going to make my board too messy, but I can do it with my finger. So its field line would look like this, and at the point where Q is, again, it would point directly between Q7 and Q6. But being a negative charge, its electric field vector points toward this negative Q6. And so doing that, its field vector would point something like that. Okay. Q5, same thing. It's a positive charge, so its field vector would point away. Okay. Q4, it's going to again point toward, but again directly along the line, joining the test charge to the source charge, more or less. Okay. Q3, radially away once again, so trace along here. Radially away is going to be like that. Okay. And then Q2, radially along, sort of like that. And finally, Q1 is going to point radially along, but pointing toward the negative source charge. Okay, and so that all 7 of those are electric field vectors at this point in space. Now, the electric field exists everywhere in space. Absolutely, I said that a little while ago, and behind here as well. But for my present purposes, I don't care about the electric field anywhere else. I only care about the electric field at this point because that's where my test charge is. Okay? So, for that reason, and that reason only, I draw only as much electric field as I need in order to do the calculation that I want to do. Okay? Sorry, there was a brief interruption there. So what I want to do then, having established the existence of these electric field vectors at the location where our test charge is, I want to then, of course, calculate the force that the test charge experiences due to all of these source charges. Now, we've talked about that before, but the new things that I'm introducing here, two new things. One is that I've got a whole bunch of source charges here, not just one or two, and as well as a mixture of positive and negative. But the other thing is that I'm starting to ask the question about the electric force from the or using, I guess, the concept of the electric field that the source charges have created at this location in space. Once again, please remember, the electric field that these source charges create, the collective electric field exists everywhere in space, including out in front of the board, out behind the board, a three-dimensional phenomenon. But at this moment, I'm only interested in the total electric field at this location in space. Okay? Which, to emphasize that point, I'm going to define or label, I guess, the point in space where our test charge is located as the point P. And I will even make it clear that this is three-dimensional by saying P has coordinates X, Y, Z. You got to choose a coordinate system, put it anywhere you want. Hardly matters at this point. Sorry. X is going to come out of the board, Y this way, Z this way. That probably doesn't mean a whole lot to you just yet. Don't worry about it too much. We'll do the coordinate system in more detail when that time comes. The issue is simply this point in space where our test charge is located has coordinates X, Y, Z relative to our chosen coordinate system, as do, incidentally, each of these individual source charges. And so the question at hand is, let's calculate the force on capital Q due to all 7 of these source charges and see where the electric field pops in as a consequence. All right. So we have 7 source charges. And I'm going to let capital N represent the number of source charges that we have, in this case 7. Okay? In the general case, we can have an arbitrary number of source charges. In that case, I can write that the total electric force is gotten by adding the electric force on Q due to the first source charge, Q1, little q1, call that F1, and then plus the force on it from Q2, from source charge Q2, plus the force on it from Q3, and so on all the way up to the force on it from Q7. Okay. To be explicit, though, for each one of these forces, well, F1 is K. Remember, that's the electric field, the electric force constant, 8.99 times 10 to the 9th Newton meters squared over Coulomb squared, if I recall correctly. Okay. K times Q1 times, let me do it in this order. So capital Q, that's our test charge. Little q1 is our first source charge. And then, and now I got to label a thing before I go any further. And the denominator, of course, would be the square of the distance between the charges. So let's do that. Let's label that. Okay, so let's see. This, the distance between Q1 and capital Q is that distance there, a perfectly straight line. I love that. Okay, and this distance here, let's see, let me label that R1. R for distance, 1 because it's charge number 1. Meanwhile, the distance between Q7 and our test charge will be this. And you'll notice I am, no, never mind, that was fine. No, ignore what I was just starting to say. Okay, might as well call this one R7. And this one here, from Q4 directly to the charge, call that one R4, and so on. Okay, all of them labeled in that way. So the R1, R2, R3, those are all simply distances from the source charge in question to the test charge. And so that is what I will put in the denominator of my force calculations over here. Okay, so the force on capital Q due to Q1 is going to be R1 squared. Okay, now I need to go back again. What direction does this force point? Well, it will turn out, and I'll explain this in a little while, but it will turn out that the force on our test charge will point in the same direction. No, I better not say that. Well, let me do it like this. If you look at each of these, so remember this electric field vector here is the electric field from Q7. So Q7, and that one there is the field. You'll notice that this field vector points exactly parallel to R1. Okay, for R4, its electric field points directly parallel to R4. R1 points, I'm sorry, electric field from Q1 points directly parallel to R1, so on and so on. And so there we are. The way we would say it in English is that the electric force on Q1, it points either directly toward or directly away from Q1, and we can figure that out real quick. Since capital Q is positive and Q1, our test charge Q1 is negative, they're going to attract each other. So capital Q is going to be attracted to Q1, and so therefore the force on it is going to point directly towards Q1. Okay. In other words, the direction of the force is parallel to R1. The force on capital Q due to little q4 is directly parallel to R4. The force on capital Q from Q7 points directly away, but still exactly parallel to R7. And so the direction for the force from R7 points that way. The force on Q from Q1 points that way. The force on Q from Q4 points that way, but we can't say that away in a mathematical equation. So instead what I'm going to say is this force is going to point in the R1 direction. This one is going to point in the R4 direction. This one is going to point in the R7 direction, and similar arguments for all the rest of them. Okay, so we will label it so. So this first force is going to point in the R1 direction, and I've mentioned the unit vector to you before. Putting this hat on it is your warning of what the interpretation of this symbol is. It points that way. So R1. So this force here, this stuff inside parentheses, that's the magnitude of the force, and the direction of the force is that way, in the direction of R1. Similar statements for the others. KQQ2 over R2 squared R2 hat plus k. I don't really need the parentheses here, but I'm sort of emphasizing. And in fact, you know what I think I'm going to do? I'm going to go ahead and put them in this light color here so that you don't pay too much attention to them, because I'm going to get rid of them in the next line anyway. Test charge, third source charge, R3 hat, all the rest of them, plus finally, just to write it, KQ times the final one, which is Q7 over R7 squared, R7 hat. Do that. Here. Okay. That's an awful lot of writing. Surely we can condense this, and if you think back to your math class and remember the summation notation, I can write this as the sum from j equals 1 to 7 of k, q, q sub j over r sub j squared, r sub j hat. Okay? So, pause the recording, stare at this, convince yourself you understand what this means. And then when you're confident about it, resume the playback. Okay, you're back. Yay. Okay. I'm going to take this one step further here. And I'm going to notice that the test charge appears in every one of these terms, so it's a common factor. And so I can factor it out. And for that matter, the value of, although the value of q sub j, the value of r sub j, those all, of course, depend on which particular value of j you're talking about. So j is just the index variable, right? But q, of course, doesn't, q is the same for every one of these terms. So I can pull it out of the summation entirely. The same is true for the k also, but for various reasons, I'm going to leave k inside the summation. So I simply write this as, so the net force then is the test charge times this summation. All right. So that's pretty good. And in fact, what I have constructed here, now one thing you'll notice, by the way, is that I replaced 7 with n because after all, n is equal to 7. The reason I did that, of course, is because this way I can generalize this result to an arbitrary number of source charges. Okay, so this is essentially just Coulomb's law. Right, so this is just Coulomb's law written for a whole bunch of charges, not just one source charge, but still only one test charge, which is fine. But what about the electric field, Kevin? That's what this is all about, isn't it? Yeah, it is. All right, here's what I want you to notice. I commented a moment ago in justifying pulling the test charge out of the calculation that its value is the same for every calculation of force for each test charge, each source charge. In other words, capital Q, the value of capital Q, is a constant for every one of the terms. It's independent of these terms, and therefore I pulled it out. So now if I take the next step, well, what if I got rid of capital Q entirely? Now, I can't just throw it out, but suppose I divided the right-hand side by capital Q. That would cause capital Q to divide away, and then I'd be left only with this summation here. Well, I can't just divide the right-hand side. I have to, in order to keep this inequality, to maintain this equality, I have to divide the left-hand side by a capital Q as well. That's all right, I'll do that. The whole purpose of my next step is because I want to eliminate the test charge from consideration. So if I divide both sides by Q, I get F, which is the net electric force on capital Q, divided by Q, then simply becomes this summation. Okay. And this construct now has the property that I want, which is it makes no reference at all to the test charge. This thing is a property, or a calculation of, I guess, something to do only with the source charges. The test charge for this stuff on the right-hand side has nothing to do with the test charge. And this thing here on the left-hand side, it looks like it has something to do with the test charge, but it really doesn't. Because remember what capital F is. It's the force on the test charge. But if I take the force on the test charge and divide that by the test charge, then the reference to the test charge in the numerator is literally canceled out by dividing out by the test charge in the denominator. And so this whole thing then is a property. This entire calculation is a calculation of a property of only the source charge. And that, of course, is what I've been talking about, and that is the electric field of the source charges. Okay, so I have then accomplished my goal, or at least the first part of my goal, which is we have in previous recordings, I gave you a sense of what the electric field was as a physical matter, and then I said, okay, can we put some math to that? And this is the first and most important step of doing that. So the next step, of course, is to take this and do a few examples with it. That'll be next.